If I asked you what the most mysterious feature of Venus is, what would you say? Its super dense atmosphere? The hellish heat of its surface? No, you'd be wrong, my friends. According to planetary scientists, Venus's craziest quirk is its rotation, incredibly slow and retrograde. While all the other planets in the solar system except Uranus spin on their axis in the same direction they orbit around the Sun, Venus defies all logic by rotating in the opposite direction. A cosmic anomaly that has baffled generations of astronomers since the 1950s. Now follow me through this video and let's try to figure out together just how far we are still from solving this puzzle. Ready? Just a moment, guys. Only 13% of subscribers know when we publish new videos. Make sure you subscribe and turn on the notification bell, because without it, you'll miss formats and documentaries you won't find anywhere else. Venus is a planet that loves to do everything backward. First of all, it rotates on itself in a retrograde direction. In other words, it spins the wrong way relative to the Sun and most of the planets in the solar system. Viewed from the north celestial pole, its rotation is clockwise instead of counterclockwise. This unusual behavior comes from the fact that its rotation axis is almost completely upside down, tilted more than 177 degrees relative to its orbital plane. But it's not just about direction. Venus also rotates incredibly slowly. A single complete turn on itself takes nearly 244 Earth days, longer than the 225 days it takes to make a full orbit around the Sun. At the equator, the surface moves at just over 4 miles per hour or 6 kilometers per hour, and you could walk at a brisk pace to stay perpetually on the terminator. On Earth, for comparison, a point on the equator moves at 1,040 miles per hour or 1,670 kilometers per hour. This backward rotation has surprising consequences even for anyone who could, absurdly enough, observe the sky from Venus's surface. The Sun wouldn't rise in the east and set in the west, as we're used to on Earth. It would do the exact opposite. And there's more. Even though Venus takes about 225 Earth days to complete an orbit around the Sun, only 117 days pass between one sunrise and the next. The reason is that while the planet slowly rotates on itself in a retrograde direction, it's also advancing along its orbit, and the two motions end up shortening the solar day. So the same point on the surface returns to the same position relative to the Sun after just 117 Earth days. For decades, the standard explanation for Venus's retrograde rotation was relatively simple. During the final stages of planetary formation about 4 billion years ago, a massive object, probably a Mars-sized protoplanet, slammed into Venus with enough force to flip it completely, reversing its original rotation. Early computer simulations suggested that a sufficiently large impactor could do the job, transferring enough angular momentum not just to slow Venus's rotation, but actually reverse it. An oblique impact with an optimal collision angle could have flipped the planet without completely destroying it or stripping away all its atmosphere. But there was a problem with this seemingly simple theory. Such a catastrophic impact should have left obvious traces: orbital debris, asymmetries in the internal structure, anomalies in the crust's composition. Yet radar observations of Venus's surface made by the Magellan probe in the 1990s showed none of the scars you'd expect from a giant planetary impact. The surface seemed relatively young, only 300 to 600 million years old, which means any evidence of an ancient impact would have been erased by intense subsequent volcanism. This paradox pushed scientists to look for alternative explanations, and this is where things get really interesting. The atmospheric tides theory. In 1997, Alexandre Correa and Jacques Lescar of the Paris Observatory proposed a revolutionary theory. Maybe Venus was never hit by a giant impactor. Maybe its rotation gradually reversed over billions of years due to intense atmospheric tides. Here's how it might have worked. Venus's atmosphere is incredibly dense, 93 times more massive than Earth's, and composed mainly of carbon dioxide. When the Sun heats this dense atmosphere, it creates huge atmospheric bulges on the planet's day side, similar to Earth's ocean tides but much more powerful. These atmospheric bulges aren't fixed but rotate along with the atmosphere, which on Venus undergoes superrotation, While the planet rotates slowly, the upper clouds circle Venus in just 4 Earth days. This superrotation creates continuous drag on the planet's surface through atmospheric friction. But there's more. The Sun also exerts direct gravitational tides on Venus's solid crust, creating bulges in the rocky surface itself. The combination of atmospheric tides and solid tides acting over billions of years could have gradually slowed Venus's original rotation to a complete stop, then reversed it. Curie and Lascar simulations show that this tidal flip process is not only possible but probably inevitable for a planet like Venus, orbiting so close to the Sun, just 0.72 astronomical units, with such a dense atmosphere, and without a large moon to stabilize its rotation, the way the moon does for Earth. This process would have been incredibly slow, hundreds of millions or billions of years, but inexorable. Venus would have gone through several phases: an initial normal prograde rotation that progressively slows down, a period of almost no rotation when the planet is locked in resonance with the Sun, and finally the reversal toward the current retrograde rotation. This theory has a major advantage. It doesn't require improbable catastrophic events, but is based on physical forces we know are at work on Venus today. It's a deterministic process, almost inevitable given the planet's conditions. But it also has a big disadvantage. It doesn't explain why Venus's rotation is so slow. Curie and Lascar's models predict that Venus should have reached a state of synchronous rotation, like the Moon relative to Earth, always showing the same face to the Sun. Instead, Venus rotates slowly but continuously. Why? The answer might lie in a delicate balance between opposing forces. In 2001, planetary scientist Alessio Gallo proposed that Venus's current rotation represents a state of dynamic equilibrium between two opposite tidal effects. On one hand, solid tides caused by the Sun's gravity tend to slow Venus's rotation further towards synchronous rotation, where the planet would always show the same face to our star. This is the same process that locked the Moon relative to Earth. On the other hand, atmospheric tides generated by solar heating of the dense atmosphere tend to accelerate the rotation in a retrograde direction. The atmospheric bulge on the day side is slightly offset from the Sun-Venus line due to the planet's rotation and atmospheric inertia. This misalignment creates a torque that pushes the planet to rotate faster in a retrograde direction. The result is a cosmic tug-of-war. Solid tides pull in one direction, atmospheric tides pull in the other, and Venus's observed rotation represents the balance point between these opposing forces. Changes in the atmosphere, density, composition, wind speed could shift this balance, explaining why Venus's rotation might vary slightly over geological time. This theory is fascinating because it implies that Venus's rotation isn't static, but dynamic, an ever-evolving balance between atmosphere, crust, and tidal forces. Precise observation of Venus's rotation over decades could reveal subtle variations that would confirm this hypothesis. A hybrid theory: impact plus tides. But the impact theory isn't dead. In fact, increasingly sophisticated simulations conducted over the last decade suggest an increasing synthesis. Maybe both impact and tides play crucial roles. In 2012, Kentaro Sugiyama of the University of Tokyo proposed that Venus might have suffered a major impact during its formation that drastically slowed its original rotation, but didn't completely reverse it. This initial impact would have brought Venus into a state of very slow rotation, then making it vulnerable to atmospheric and solar tides. In this scenario, the impact did the heavy lifting, slowing the rotation from perhaps a few dozen hours, similar to early Earth, to a few days or weeks. Then, atmospheric and solar tides completed the job over hundreds of millions of years, gradually reversing the rotation and bringing it to its current state. This combined theory better explains the observations. The impact explains why Venus rotates so slowly compared to Earth despite being twin planets, while the tides explain the retrograde reversal and the dynamic equilibrium state. Simulations show that an impact with an object of about 0.3 to 0.5 Earth masses, smaller than previous estimates, hitting Venus at an oblique angle could have drastically slowed the rotation without destroying the planet or stripping away the atmosphere. Debris from the impact could have formed a temporary moon that later crashed back into Venus, leaving few permanent geological traces. The climate consequences of slow rotation. Whatever the cause, Venus's retrograde and incredibly slow rotation has dramatic consequences for its climate, consequences we're only beginning to understand. On a rapidly rotating planet like Earth, the Coriolis effect, the deflection of atmospheric movements caused by rotation, dominates atmospheric circulation, creating the westerlies, polar jets, and tropical cyclones. But on Venus, where a complete rotation takes 243 Earth days, the Coriolis effect is almost non-existent. This explains why Venus's atmosphere can develop extraordinary superrotation, without Coriolis forces fragmenting the atmosphere into multiple circulation cells. The entire atmosphere can rotate as a solid body, accelerated by atmospheric waves that transport angular momentum from equatorial regions toward the poles. Slow rotation also has a profound effect on heat distribution. On a rapidly rotating planet, rotation tends to distribute heat evenly between the day and night sides. But on Venus, with its months-long days, you'd expect huge temperature differences between the sunlit side and the dark side. Instead, surprisingly, the temperature on Venus's surface is nearly uniform, 464 degrees Celsius or 867 degrees Fahrenheit on both day and night sides, at the equator and at the poles. How is this possible? The answer lies in the extreme greenhouse effect in atmospheric circulation. The dense CO2 atmosphere traps heat so efficiently that even the night side stays scorching hot, while high-altitude winds, blowing at 224 miles per hour or 360 kilometers per hour, transport heat from the equator to the poles and from the day side to the night side. Slow rotation might also have profoundly influenced Venus's geology. On Earth, rapid rotation contributes to generating the magnetic field through the dynamo effect in the liquid core. On Venus, the incredibly slow rotation might be one reason why the planet doesn't have a significant global magnetic field. The core rotates too slowly to sustain the convective currents necessary for the dynamo. Without a protective magnetic field, the solar wind has eroded Venus's atmosphere for billions of years, stripping away water the planet might have possessed in the past. The atmospheric erosion process might have been accelerated by slow rotation, creating a catastrophic feedback that transformed Venus from a potentially habitable world into a toxic inferno. The solution must be found on Venus. As Venus continues its slow and backward journey around the Sun, the planet still guards the secrets of its turbulent past. Was it a catastrophic impact that flipped it? Or were the relentless atmospheric tides that gradually reversed its rotation over eons? Or perhaps a combination of both, in a cosmic dance between catastrophe and inevitability? The answer might lie in 12 to 19 miles or 20 to 30 kilometers below the sulfuric acid clouds, in the depths of the atmosphere where temperature and pressure make carbon dioxide supercritical. Or it could be buried thousands of miles below the surface, in the remains of an ancient impactor still distinguishable after 4 billion years like a cosmic fingerprint. Until we send probes into Venus's depths and precisely measure its gravitational field, internal structure, and rotation variations, Venus will continue to spin backward, defying our certainties and reminding us how much we still have to learn about the fundamental mechanisms that govern planets. Okay guys, so what do you think? Did watching this video raise any doubts or questions? If so, it would be strange if it didn't. Please feel free to let us know in the comments. And if you want to learn more, check out the other video about Uranus, the other planet with a decidedly strange rotation.